introduction. Most people are probably familiar with our solar system. We've got Earth, you're very familiar with its surrounding planets. You've got great big Jupiter and Saturn with its well-known rings, and then much further out, you've got Uranus and Neptune. And then what I'm really going to be talking about, and what's much more important to me, is these belts of small rocks in between the planets or outside the planets. So the asteroid belt in between Mars and Jupiter, and then the Kuiper Belt much further out. So yes, the solar system is a very big place. I did take the time to make these planets be to scale to each other. This yellow line you can see along the edge, that's actually how big the sun is relative to all our planets. So if we zoom out a little bit, you can see we are quite small up here. And although the sizes of these things are scaled to each other, the distances are not, because the screen is not physically big enough. If the sun up here is roughly 2 meters across, if you want to get to the closest planet, Mercury, on this scale, you have to go all the way to the other side of that big telescope you've seen outside. If you want to get to Earth, you have to go all the way down to that big green building you passed on your way up the hill. If you even want to get to Jupiter, you're going as far as Prospect Lake. Neptune, much, much further. It's about 6 kilometers away on this scale, so you're talking as far away as Mount Douglas. So space is very large. Most of it is empty. It is called space for a reason. But the solar system didn't just pop into being as we see it today with these lovely planets and the great big sun. Very many years ago, or about 4.6 billion years ago, it was instead a planetary nebula. This is a photo from HST of a different planetary nebula, which hasn't yet formed into a solar system. But this is just a great big sphere of gas and dust, which is the materials that are used to build planets and stars, but haven't yet happened. At some point around that time, we had some disturbance go off nearby. Most likely a star exploded nearby and disturbed our big cloud and started the creation of our sun. And of particular interest for us in terms of the planets, this big disk now of gas and dust. So this big disk, this is where our planets were born. And similarly to how we didn't just get the solar system as it is now, the planets didn't just appear into being, they kind of formed slowly. So if we consider this to be the gas and dust they formed out of, as they travel around the disk, they start to clump together into these little pebbles. Over time, the pebbles themselves start to clump together, and then once we're big enough, we start getting gravity joining things together, and eventually on a much larger scale, you get planets themselves. And the planets we see today, those kind of tells information about the conditions that they might have formed in. So for example, close to the sun, we have rocky planets, because this area was hotter, so you didn't have as many ices, it was just rocks. Beyond the ice line, you were able to form big cores because you had water ice, methane ice, creating the cores of these big gas giants, and so they could gather the lighter gases like hydrogen and helium. So you get these big giant ones, and then further out still, you've got ice giants. So these are giants made of ice because it's very cold and distant out there. And that's not all the story. The planets and their layout and how we see them today isn't, again, how they formed. We believe that they formed in a much more kind of compact layout, so Jupiter and Neptune would have been much closer together. We think there would have been 3 ice giants, not just 2. And after some interaction between the planets, it would have set off what we call planetary migration, where we've got Jupiter going in and then out, and all the rest of the planets going out, and we just lose that ice giant entirely. And this is more like what we see today. But I guess it's one thing to say all this happens, but how do we actually figure it out? How do we figure out how these planets have come together out of other rocks? Why do we think there was ice lines? Why on earth do we think the planets migrated? Because if you just look at this as a picture of Mars and a picture of Jupiter, if you just straight up look at these as planets, you can't really say that much about, oh, where this has been before, what sort of rocks would have made it up. Like, the real question we want to ask here is, how are we tracking these planets? To kind of understand this, it's quite similar to what we actually do on Earth. So tracking on planets has similarities to tracking planets. If you take, say for example, this is a wildebeest. If you just look at one, maybe a couple of animals, you can have a look at like the dirt in its feet and go, oh, it's been in a particularly muddy area, in the same way that you can look at Earth and its meteor crater and say, oh, it's passed by other rocks in space. but there's a limit to how much information you can find by just looking at one or two animals. If you really want to see the bigger picture, you have to look at the environment that they've influenced in their passing through. So we know that animals have migrated through this area because they've left paths, they've disturbed the smaller rocks and grass and dirt and left traces of their path through it. And in a similar sense, the Kuiper Belt and the asteroid belt show these traces of where the planets have passed and how they've formed as we see them today. So this is a pretty updated showing of all the bodies we know of in our solar system. I downloaded this 2 days ago. So this isn't everything that exists, but it's everything we've discovered so far with the planets where they were 2 days ago. So you can see the Kuiper Belt out here beyond Neptune is made up of these little yellow dots, where Neptune is again just a blue circle. And if we zoom in inside of Jupiter, in between that and Mars, we have the asteroid belt, which is made up of lots and lots more rocks. Well, it's not so much it's made up of more rocks as it's easier to find things because they're closer, because these are rocks and gatherings of ice and dust, which is that they're not like the sun, they're not radiating their own light. We can only see them because of the sunlight they reflect back to us. So as things are close to the sun, they're easier to see. If they're further away, they're dimmer and therefore harder to see. So we want to study the small bodies in our solar system to figure out how the planets formed and where they came from. For that, you can actually start pretty close to home. The Moon has a tracer of the environment it's passed through. It's only a little bit younger than the Earth, and you can see the layers of cratering at the surfaces, and we've visited the Moon, so you can pick up samples. And I mentioned earlier about how the planets migrated. Jupiter went inwards and outwards. Part of the evidence of that is like a lot of craters in the Moon look like they may have happened at the same time, which suggests that there was more material passing past it and impacting it in that time. If you travel a little bit further out to the asteroid belt, so these are in between Jupiter and Mars. These are a couple of asteroids that, again, we've successfully managed to visit. If we start with the bigger one here, this is asteroid Bennu, which not that long ago they sent a mission out called OSIRIS-REx, which touched down on the asteroid, gathered up the rocks, and has since delivered them back to Earth, so dropped that sample capsule back to Earth, and the spacecraft itself has actually continued on to visit another asteroid, which is also pretty cool. But asteroids like this object is not just one giant rock. We call them rubble piles. They're really just gatherings of like gravel, which are held together loosely by gravity. The best way to kind of describe the consistency of it is if you've ever had a large container of popcorn and you kind of stick your hand in it, they hold together in a similar way. Another interesting asteroid is this one here. It's called Didymos, and this is a system, so it has its own moon. Originally, it was called Didymos and Didymoon, but NASA decided to send a mission to them, so they had to give it a cool NASA name, so it became Didymos and Dimorphos, which I think is less fun, and I think it should still be called Didymoon, but that's a different thing. But the mission to this object was particularly interesting because they were trying to see how you'd redirect an asteroid. And as it turns out, the way they wanted to test was by just smashing straight into its moon and seeing what happens. Yeah, so that's the stream that they got from the spacecraft before it was vaporized in the impact. Interestingly, not included in this particular GIF, but the very last image is just like an inch at the top and the rest is blank because the instrument just ceased to exist while it was transmitting that out. But yeah, so the point of this was to see, okay, how solid actually are these things if we fire something into them, how much they break apart, and such things. So this is a nice little GIF of which was taken with HST, so the Hubble Space Telescope, showing not too long after the impact, the one in the top corner that was taken from Earth, and you can see, although to be clear, the dot in the middle is the entire system. You can't see the individual moon from Earth, it's too small. But from the whole, if you look at the whole system from Earth, you could see that massive cloud of gas and dust coming off after the impact. And you could also measure to see how much the orbit and things changed, and that tells you more about how these things are put together in terms of their little pebbles of rock. Of particular emphasis, and I'll probably talk in a bit more detail about this, is what we call Trans-Neptunian Objects, or solar system objects that are out beyond Neptune. I've also included on this slide comets, because although comets tend to reside where that green arrow around Jupiter and Saturn is, they come in closer, or at least they're seen closer. They started life similarly to how these trans-Neptunian objects did. They've just since traveled inwards and therefore changed. But the reason why trans-Neptunian objects, so this big one here called as Arrokoth, are interesting is that they are very far away from the sun. Nothing really interacts with them other than them rotating and a little bit of gravity if their orbits change. Which means that they're the best way to study how objects formed in the early solar system, because they formed into these shapes and haven't really been disturbed since. And like I mentioned earlier, it's harder to see smaller things when they're further away. So comets come closer. So if you actually put those at scale to each other, you can see that the comet is much, much smaller than Arrokoth. Similarly, if I put in that asteroid Bennu from earlier and bring that down to the same scale, you can barely see it anymore. So in the Kuiper Belt, we tend to see objects of this sort of size, but it's not because there aren't smaller ones, it's just we can't see them, they're not bright enough. But we're pretty sure they're there, based on the fact that these comets come in and they're smaller and such things. But yeah, comets are a good way to study what's making up these objects in the outer solar system, because they formed in the same conditions, and now they come in close enough for us to actually see. This one's comet 67P, because they tend to usually have quite boring number names. But because they travel close to the sun, the ice and the rock that makes up their surfaces specifically the ice starts to sublimate, puffs out like you might say steam coming off water. In a similar way to that, you've got ice sublimating off the surface of these objects, and it kicks up dust, and you get these craters from where the dust has come off. But you can study the surface and the dust around it and ask the question of, wait, what are these objects actually made up of? Another object which lots of people have heard about in the Kuiper Belt is Pluto. So this is Pluto over there, and it's moon Charon over here. And it was fairly well known for previously being a planet, but is no longer a planet. And believe it or not, there is some good reasons for it no longer being a planet. One of those reasons is that the way they've defined planets now is that it has to have cleared its orbit. So in the same way that Earth travels by itself without similarly sized objects, Pluto doesn't do that. It travels in the Kuiper Belt. In the Kuiper Belt, there are actually more dwarf planets out there with it. So for that reason, it's currently not a planet. Another reason is actually shown by this wee GIF in the middle. You can see Pluto in the middle, and then it's moon Charon orbiting it. The problem is it's not really orbiting Pluto. You see the wee white cross in the middle, that's the center of their rotation, so they're really orbiting each other. That center rotation isn't inside Pluto, it's just outside, so it's a system orbiting the sun, not a planet orbiting the sun, so again, dwarf planet. But it's still pretty cool, and that's the New Horizons mission flew past it and got some lovely pictures. But the New Horizons mission is quite good because it also, by chance, flew past Arrokoth. So you'll see this picture a lot because it's the one good picture we have of a Kuiper Belt object. It's the only one that we've flown past. But even just looking at one object helps us figure out if our theories of how these things are coming together is correct. So are we really making bigger objects out of smaller objects? And from Arrokoth, it kind of looks like that's the case. So if you have a look at the object by itself, you can see, hopefully you can see it on the screen, it's made up of these different kind of like regions, which you can convince yourself would once have been kind of soft boulders, which have smooshed together into these bigger boulders. And then obviously the object itself is made up of two big kind of boulders smooshed together. So that, you would say that's probably reasonable supporting that objects are made by smaller objects coming together. So the outer solar system is useful. It's also cool because having visited Arrokoth, we were able to confirm one of the other ways we look at objects, which is something called occultations. So keeping in mind that there's lots and lots of stars in the universe and there's lots of small objects in the universe, at some point these small objects will pass in front of stars. And depending on where you are on Earth, you're going to see it passing differently. So in a much simpler version of it, if you picture this being stars and one giant object passing in front, how long the object, you can no longer see the stars, it depends on how much of the object passed in front of it. So for Arrokoth, from one place on the Earth, you're going to see the star and it never changes in brightness. You might see it and it drops, but it's not for that long. Or if you look at higher up, it's dropped in brightness for a long time, which means that you're crossing a long bit of the object. And if you actually put those on top of each other, it's pretty effective, isn't it? So that's pretty cool. So that's how objects are formed. But then the other question is, using the vast number of objects that we've kind of discovered in the outer solar system and use those to track planet migration. So we can do that using the orbits of objects. So if you see a plot like this, there's the same major axes along the x-axis and what's called eccentricity on the x. We've got Neptune down here, which is about 30 AU, and I've highlighted just one object to show you what an orbit looks like. So this particular object has a same major axis, which is just the longest distance across its orbit. It has an eccentricity, which is how circular its orbit is. And then what I didn't show in the plot is that the orbit is also often at some inclination relative to the rest of the planets, which you can see down in that bottom corner. And you have lots of different objects in the Kuiper Belt on different orbits. So you have a slightly more cool one here, which is a higher eccentricity, so it's more oval, it's got a higher inclination. You have one of your really extreme ones, which travels really far away, but has a more oval orbit, which means that you can see it whenever it comes nearby. And it's also probably quite interesting to know that whenever we see these really distant objects, you only see them when they're nearby. We know that they spend time far away, they spend most of the time far away, but you can only see them whenever they're coming in and around Neptune. That's part of the reason why you tend to see objects only at higher eccentricity in the distance. Another part of that reason is that beyond this, what we call classical belts, this big concentration of objects down here, beyond that, it looks like there's a gap in how many objects there are. We're not entirely sure why, we're not entirely sure if it's true, but as far as we can tell so far, there seems to be no objects past that, and that's trying to recreate this structure as we see it in the Kuiper Belt helps us figure out how the planets migrated. The reason for that being that we know how gravity works. We know how things might be carried by planets. And when I say carried by planets, I'll show it in a sec of you have objects moving as the planets migrate. So in the same sense that if you sit on a chair and you throw a heavy ball, your chair will move backwards. As Neptune passes past objects, it'll throw them inwards and travel outwards. Some of the objects just get carried out by it. So although we've probably lost a lot of material, we end up with the Kuiper Belt, which, if I go back a little bit, you can see is made up of a mixture of objects that formed far out and didn't really move, and objects that formed further in and came in overlapped with those objects that are far out. So hopefully you're convinced that the solar system is interesting and we should study the small bodies. So we'll just finish up with what do I actually study in the outer solar system, the stuff which is coolest. So I study the colors and compositions of TNOs. So obviously it doesn't actually look like this. I've taken one picture and recolored it, but it hopefully gives you a vague idea. So I've spent most of my PhD investigating where these different surfaces and colors of objects came from in the early solar system and what that might suggest for future discoveries. So when I talk about colors and compositions, what does that actually mean? You guys may have seen pictures of what we call spectra before. This is the only picture I'll show of them, so don't worry too much, but it's wavelength, so your wavelength of your light versus how much the object reflects that light. So if it has a certain material on its surface, it might absorb light at that wavelength, so you get a dip in the reflectance, versus if it doesn't have any materials, it just stays the same. Unfortunately, to get these, what are quite beautiful spectra, you need a lot of time on a lot of big telescopes. These were taken with JWST, which is very difficult to get time on. So if you want to study lots and lots of objects, you instead use what we call as colors. So what that means is instead of taking lots and lots of little bits of wavelength, you just take these big bins of wavelength, and you can still figure out what's going on with the spectra based on this. So say, for example, it's dimmer over here and it's brighter over here on its spectra. In the same sense, your R band will be dimmer than your G band and similar with R and J. This is typically shown in what we call a color plot. So this is just that same G and R from the previous slide. So this G and R, G minus R, so how bright it is in G versus how bright is it in R, and then the same for R minus J on the y-axis. So this is from a color survey which I did a lot of work with, of about 100 TNOs. You've got this star shows what color the sun is. So all of these objects are more red than the sun, so if you travel along the x-axis you get more and more red. Why those pictures I showed of Arakoth were kind of greyish red, that is genuinely what color we think it is. But historically, you can, once you have a look at these, you can actually split them into different groups. We'll often refer to these as bluer and redder. They are all red, but blue is relatively less red, so it's a nice color to put in the plot. As we've got more observations, we've realized you can actually split these even better based on the spectra. So all along this particular red line, it means that as you travel from G to R to J, you have a single straight line. If it's below the line, your J band, your longer wavelength, is relatively dimmer. So you're fainter at your near IR wavelengths. If you're above the line, you're relatively brighter at those longer wavelengths. So therefore you call them faint IR and bright IR. It's not full spectra, but it's still telling you the information that you get on the spectra. The reason why this is kind of important and interesting in terms of the origin of our solar system is that we think that these colors we see today are a result of where the objects formed in the early solar system. So all of these different things came from different places in this disk that was around Neptune. It's obviously a much more simplified schematic. This is a bit more like what I showed it earlier. So this massive planetesimal disk of white dots is the same as that grey box. Further out, we had objects that kind of formed where they are and haven't really been changed. It's the red box further out. And we think that those colors that we see today, that's a result of where in this disk they were, and you can investigate, oh, where could these have gone? Or similarly in terms of faint IR and bright IR, the slightly more modern definition. And you may have a question based on these graphs of, oh wait, Laura, that disk just stops and there's a gap. Why on earth is that the case? That is because Neptune is where it is today. Neptune moved outwards by displacing objects, but Neptune had to stop at some point. Well, it stopped where it is today, which means that either it ran out of material to displace, or the amount of material that was there dropped significantly enough that Neptune can no longer move outwards. So we have something like this top layout where you had just a gap material, a bottom one where you just have a lower density material. I investigated both because you may as well. But yeah, but what does that actually look like? So I call this a color simulation because it's all happening inside of the computer. You have your disk around Neptune. You can give it colors with that split in color, dependent on how far it is from the sun. You can let all of the planets migrate and displace all these objects until you end up with the Kuiper Belt as you see it today, of this jumbled mixture of different surfaces. And then you can ask the question of, okay, does it match the observations? This is slightly more complicated than just doing a direct one-to-one comparison. You can't just look at how many you have of one, how many you have of the other, because when we look at the Kuiper Belt, we're not seeing everything. So you may have noted when I put this up earlier that you have some weird concentrations of objects. This one down here is usually fairly obvious. It's a nice one to point out because it's not that there's more objects there, it's that Pluto is there. So when New Horizons happened, we pointed lots and lots of telescopes in that direction, as a consequence discovered more objects in that direction. So anytime you do a survey, you're only picking at some of the objects. But on the bright side, as we do this survey, you take really good track of where your telescope's pointing, the limits of your telescope, like how bright an object can this telescope actually see, and you can feed all that information back into your computer and simulate what the survey would have seen. So if we go back to this one from earlier with your objects, which have been colored based on where they were before Neptune migrated, point a virtual telescope at them, you'll see what the telescope would have seen. And now at that point, you can compare to what we've actually observed. From this, I got lots and lots of numbers, but we'll only show that briefly and then go back to graphics. Because yeah, although like you can see you get different positions as to where this transition in colors could be, that's not the only factor here. You have other observational factors you can use to put limits on these values. So for example, we have objects that we know formed as these binary systems, and they formed like that. They couldn't have been displaced too far since their formation, so that puts a limit on that surface color. Around Neptune, you have more bluer or bright IR surfaces than you have of the redder ones, suggesting that the red ones perhaps were further away than Neptune. And then finally, whenever we observe the Kuiper Belt, you tend to see that at lower inclinations, so on the same disk as Neptune, you get more redder or faint IR surfaces, while at higher inclinations, so above Neptune's orbit, you get more of the bright IR ones. And that allows you to, well, allows me to work through and actually rule out some of these options. And nicely, you end up with just 2, which I have circled here, or more graphically shown like this. So this is, from that work, what we think the disk beyond Neptune would have formed like. This is just initial semi-major axis, so where those objects started, versus how many of them there were. So we start with lots and lots of objects that dropped off at about 30 AU, as in where Neptune is now, and then you would have had less. And on the interior, you would have had these bluer or bright IR surfaces, and the exterior, red or faint IR. And that, again, tells you more stuff about how the solar system formed. It means that the objects that formed further out likely share a surface with those that formed further in and got displaced outwards. But they were just on the outside of that initial disk. It might be that the reason for the different surfaces is because there was lots and lots of objects here, so they were colliding with each other and changing what the surfaces looked like, and then the planets migrated and they kept that. If there was more material further in, that might suggest that you get different sizes of objects versus further out, which is what I'm currently actually investigating, but don't have any pretty pictures to show, so we'll just leave it as a statement. But yeah, that's kind of it. There's lots of interesting stuff in the Kuiper Belt. That's just a kind of summary of what I've talked about, and yeah, thank you for listening. I think if you have any questions, we do have time for that until somebody kicks me out, I assume. Yes?
When you talk about the extra ice giant, how do we know that there was one, and why did we discover that?
Okay, the reason why we think there was an extra ice giant is because whenever you try and create the Kuiper Belt as we see it today on a computer and move all these orbits around, it's really, really difficult to create the Kuiper Belt as we see it today without that extra ice giant. People, like, it's difficult using just the 4 giant planets that we know which are the ones influencing that space. So people are of course like, it could have formed with more than this. So they would add in 1, they'd add in 2, they'd add in 3, and the best scenario for creating the Kuiper Belt as we see it today is with that 1 extra ice giant.
What about you guys trying, like, the rings on its side, right? Is that like an interplanetary something that happened? Like, why?
Oh, you mean Uranus because it's rotating sideways? Yeah, it's likely that it's been displaced in some way, and whenever it migrated outwards, it turned on its side. But what's also interesting to note there is Venus is similar to Uranus in that it's also been significantly displaced at some point. It's the only planet that rotates upside down. So it's not something that's only happening on the outside. Like, space is a big place, but they are still interacting with each other and displacing things. Uranus has been on its side for a long time, but.
So is there theory on why it is and what asteroid it is?
There could be, but not that I personally know. That people have probably investigated that, but I don't know what they found out. Any other questions? No, it's okay if not. Yeah, I guess if there's no other questions, we can just finish up. Oh, sorry, yeah.
Do you have any theories about what causes the drop off at 38 degrees?
Not really. It is, if you've ever seen pictures of other systems that are forming planets, similarly, they have bands around the stars. They've got concentrations and drop-offs and concentrations and drop-offs and so on, which planets are forming. So it's likely there's some instability happens and it causes material to gather together and maybe form a planet, maybe not form a planet, or just stay as a belt. But what causes them, it's difficult to say for certain. It's possible that like the Kuiper Belt isn't the outmost region of objects, is the limit to how far we can see. There are other people, maybe Lowell at the back of the room, he investigates if could there be another Kuiper Belt beyond the Kuiper Belt that we just can't see. Because we know how well our telescopes work pretty well at this point. We know that there is very much limits to what they can see. So yes. Any other questions? Yeah?
How cold are asteroid giants?
Very cold. It's so like it's close to absolute zero once you're further out in space, but it's also kind of weird because it's a really low pressure environment, so things don't behave the same way they would on Earth. That's why whenever you look at comets, you've got gases sublimating. There's no liquid in between. It just goes from solid to gas. It's on the order of like minus 200 or so, because that's close to absolute zero is minus 273, so it's a bit above that. So unbelievably cold, basically. Yeah, the reason like Neptune and Uranus, they're blue, but they're blue because there's lots of methane, which is the gas that comes off cow poops and stuff. Obviously the gas here, but it's an ice all the way out there. Yeah.